Welcome to 8.5 Counting Principles. We're going to talk about a few different counting principles. I would highly recommend at www.purpleshirtednerd.com. There is a video in the section, in the 8.5 section, on horse racing and counting principles, and I think it really will help clear up some of what I would normally clear up on this, but in the interest of time, I would just refer you to that video. I'm going to go through this pretty mechanically, rather than necessarily explain all of the math behind and why we use permutations and combinations. That material is covered on the video. So the fundamental counting principle, I would refer to this as a closet problem, because probably the first time you encountered the fundamental counting principle, you had a problem something like you have 5 pair of pants and 6 shirts in your closet, and then you did something like this. You said, well, I got all these 5 different pair of pants, and then from each one of those I've got 6 shirts, and then you realize pretty soon by the time we do the tree diagram we end up with 30 different outfits. And the fundamental counting principle just says if two events, if the first event can happen M ways and the second can happen M2 ways, the number of ways both events can happen, you multiply. Basically, if you see the word and, that is if I have to choose pants and shirts, it's the number of ways I can choose pants times the number of ways I can choose shirts. And implies multiplication often. Okay, then permutations, if you're selecting a group from a subgroup, let's say I have 25 students in the class and I'm selecting 6 students, that is either going to be a permutation or a combination. Then we have to determine, does the order matter? In permutation, the order matters. In combinations, down here, order that we select in does not matter. So, to reiterate that, to repeat myself, if you're selecting a subgroup from a big group, it's either a combination or a permutation. Okay, the number of permutations of n elements, it turns into this formula, and we would write, let's say we're selecting 6 out of 8 students, and we're going to put them in an order. We're going to make the order matter. That's going to look like this. That would be 8P6, or it could be written P86. This is usually what I fall back on, but the calculator really likes it this way. And that means we take the numerator, the 8, go factorial with it, and put it on the numerator minus the denominator, 8 minus 6, 2, 8 minus 6, 2 factorial. And we get 8 times 7 times 6 times 5 times 4 times 3, and the times 2 times 1s cancel. So that's how we would handle a permutation. Distinguishable permutations, I'm going to talk about those in a way that's going to make sense to you. I also have a video on that, but I'm actually going to talk about that in this video. And combinations, let's say I had combination, I'm going to choose from 8, 6 people. That could also be written C86. I like that. The book uses this a lot. Or it could be written shortcut, just 8-6, no fraction bar. And what it says is we take the numerator 8 factorial and we put that over, same as permutation up here, we put it over n minus r factorial, so over 2 factorial, but then we also multiply it by r factorial, the 6 factorial. So in this case, this would be 8 times 7, stop, the 6 on down cancels that, but we still have over 2 times 1. Always you'll be able to reduce bottom with top when you do this. 2 and 8 reduced to 4 times 7, 28. This is going to far exceed 28. Now what I like to think of is this r factorial or this 6 factorial. This is the number of ways we can order our selection. See, it's a permutation, but we don't want to count all the different orderings of those 6 we've chosen, and they're counted into 8 factorial on 2 factorial. And that's explained in a lot of detail in that horse racing video. But this little additional part, additional piece, is how many ways we can order our selection. Okay, let's take a look. We will come back and talk about distinguished permutations. Determine the number of ways in which a computer can randomly generate one or more such integers or pairs of integers from 1 through 15. So the computer generates numbers from 1 to 15, and we want to know how many ways it can generate a number greater than 11. Well, it could generate a 12, a 13, a 14, or a 15. So 4 ways. Now, this, I feel, is really up for interpretation. When they use the word distinct, what do they really mean by distinct integers? We want a pair of distinct integers whose sum is 24. Well, let's see, distinct integers whose sum is 24 from 1 through 15. 12 and 12 is an argument. Well, but I would claim they are not distinct with one another. So how about 11 plus 13? How about 10 plus 14? And how about 9 plus 15? So we could make an argument it's 3. But how about if the first number the computer selects is 13 plus 11, and the first number is 14, and the second number is 10, and the first number is 15, and the second number is 9, that would be 3 more, or maybe imply 6. Do we claim that's not distinct compared to this? I believe back of the book is here, but I think we need to really ask, give me a good definition of what you really mean in the context of this problem with the word distinct. So not a big fan of distinct unless it says distinct and gives a good explanation of what it means. Anyway, a college student is preparing a course schedule for next semester. The student must select one of 2, we got 2 math courses to choose from. We have 3 science courses to choose from, and we have 5 courses in social science and humanities. How many schedules are possible if the student must select one of those, and one of those? Well, that's the closet problem. That's like we have 2 shirts, we have 3 pairs of pants, and we have 5 pairs of shoes. If I choose one of each, how many outfits do we have? 2 times 3 times 5. I'm going to wear shoes or pants and shirt and shoes. We have to choose math and science, and those ands always imply multiplication. So we get 30. In Pennsylvania, each standard automobile license plate number consists of 3 letters, letter, followed by 4 digits. 1, 2, 3, 4. How many distinct Pennsylvania license plate numbers can be formed? Well, I have choices. I have choices for this. I can choose out of 26 letters, and I can choose out of 26 letters, and I can choose out of 26 letters, and I can choose out of 10 digits, and choose out of 10 digits, and choose out of 10 digits, and choose out of 10 digits. And I will leave that for calculator work for you, but I can abbreviate a little bit. 26 to the 3rd times 10 to the 4th. That is a lot of license plate possibilities. Okay, radio broadcast. A's going to be easy. B's got a lot going on with it. I'm going to zoom in on this just a little bit here. Okay. Typically, radio stations are identified by 4 call letters. Radio stations east of the Mississippi River begin with a W. Radios to the west begin with a K. Find the number of different sets of radio stations in the entire United States. So, 4 call letters. The first one is either a W or a K. We only have 2 choices, but after that, I have 26 choices and 26 choices and 26 choices, and once again, I'm going to leave that to calculator. 2 times 26 times 26 times 26. Now B. B is a whole nother ball game here. Find the number of different sets of radio station call letters that are possible when the call letters must include a Q. All right, so here's the deal. I've got two choices, and then I've got three, because I've got a W or a K, and then I've got three more choices after that. And one of them has to be a Q. So I could, for instance, set this to be a Q, only one choice here, and these to not be Qs. Or I could say, that's important, or, well, I'm going to choose what, K or a W, and then I'm going to not have a Q here, and I'm going to have a Q here, and I'm going to not have a Q here. Or, not a Q, not a Q, Q. Or, stick with me here, I got a shortcut for you coming up. I could have two choices here. Let's put a Q here and a Q here and not a Q there. Or, let's put a Q here, not a Q there, and a Q here. Or, let's put a Q here and not a Q, but a Q and a Q. Or let's put a 2 here and let's put a Q, and a Q. Now, important probability and counting strategy. Really important one. The more times you find yourself, hey, we could do it this way or this way or this way or this way, the more you should consider the total. If we consider it a win, we consider these are all the ways I could win. I could win this way or this way or this way or this way or this way. We could take the total number of ways things could happen minus the probability I lose. How would we lose in this scenario if we don't have a Q? So that would be two choices times not a Q, not a Q, not a Q. All the other choices besides that. So the answer to B could be 2 times 26 to the third, the number of total possibilities, minus 2 times not a Q, not a Q, not a Q. Whole different process to it. And that's where it's like if you want to get from the front yard to the laundry room in the very back of the house, you could go in through the foyer and then in through the great room and then go past through the living room and back through a bedroom back to a foyer. You know, or you could just try to sneak in through the back door here. This is a much simpler approach, but it's a great strategy, and I will leave that for calculation. 26. In how many orders can 5 girls and 3 boys, so we have 8 students, or 8 boys and girls, walk through a doorway single file when there are no restrictions? So we've got 8 going through there. 1, 2, 3, 4, 5, 6, 7, 8. For A, how many choices for the first person going out? 8. There's no restrictions. Then 7, ... That just becomes 8 factorial. That is actually equivalent to permutation 8, 8. We're going to choose 8 out of 8 and P, permutation, the order matters. Calculator. B, the girls walk out before the boys. So how many choices for the first girl? 5, 4, 3, 2, 1. And then the boys start going out. How many choices for the first boy? 3, then 2, then 1. Calculator. In how many ways can 8 people sit? Never liked the wording on some of these. How many ways can one person sit? Well, you could have right leg crossed over legs and either leg crossed. You could be sitting sideways, sitting on your knees. They're just talking about arranging them. We have 8 positions to put people in. I'm going to choose one person out of 8, and I'm going to put them in the driver's seat. How many choices? 8. How many choices for the second seat? 7. ... This is also 8 factorial. Evaluate this permutation using the formula from this section. Well, that is, see, we can call it this. We can call it P7, 4. And a lot of people will say this is permutation 7, length 4. See, this becomes 7 factorial over 7 minus 4 factorial, or 7 factorial over 3 factorial, which is 7 times 6 times 5 times 4, and the 3 on down cancels. So let's see, that's 42 times 20. That's 84 with a 0. And that would do it. The permutation length 4, 1 entry, 2 entries, 3 entries, 4 entries. Coincidentally, it just happens to start at 4. Excuse me just a moment.
I'm not coming back. Is there anything that I need to know for tomorrow?
I'll have a video and you can grab the you got it. Yep. I'll have a video out on it. Okay. Okay, excuse me. So I want to make certain that we're comfortable on this. If this was P73, I would go 7 times 6 times 5 and stop. It's permutation 7 length 3. Why? Because 4 factorial would be in the denominator. So that's another way of handling it. I like it with the length. Permutation 7 length 4. Evaluate NPR using graphing calculator. Okay, different story here. So we will grab our calculator, clear this, and I'm going to go alpha window, gets me where I can get NPR. Or if you don't have that option, you can go to math, probability, and that gets it as well. So I'm going to enter 10 and 8, and I'm in the wrong spot. There we go. Got what I need. Enter, and we've got a reasonably large number here, as we might expect. How many orders? I got 10 people to choose 8 from, and I'm going to put them in order. How many different ways can that be done? 1,814,400. Okay, how many different batting orders? So if I choose my 9 players out of 15, the order still matters. So if I'm choosing 9 from 15, it's either a combination or permutation. Because the order matters, it's a permutation. This is permutation 15 length 9. You can calculate that. I'm going to go ahead and just do that one again. Alpha window 15. Guess because I'm curious, it's a baseball thing. And once again, oh, we got a whole bunch of choices here. Surprising how quickly these things can grow. So we have 1 billion different batting orders. Again, somewhat perhaps surprising. 45 and 46, use the letters A, B, C, D. Write all the permutations, all the ways we can order them, provided B and C remain between A and D. So A, B, C, D works. A, C, B, D, they stayed between them. I also could have D first, A last, B, C. And I don't think there's any other way we could do that. Now, we actually could figure out the number, and it's really so finite, but we could figure out the number by doing this. If A and D are on the outsides, how many choices for this? 2. Once I choose one here, how many choices for this? 1. If B and C are in the inside, how many choices here? 2. Once I've chosen one there, 1. There's our 4 total possibilities. Okay. I have a separate video on this, but I'm going to go through this pretty quickly here. This goes back to that first page where we talked about distinguishable permutations. And I think this is going to help make sense out of it. So I pour out my Fruit Loops into my bowl. Haven't put the milk on yet, because you always put the milk on after you put the Fruit Loops in the bowl. And I only had 8 Fruit Loops left. 3 of them were purple, 1 of them yellow, 1 red, 2 blue, and 1 green. And I wondered to myself, I wonder how many different ways I could put these in an order and tell that they're in a different order. You see, if I switch these 2 Fruit Loops, P2 and purple 2 and purple 3, I won't be able to tell that I put them in a different order. So if they were all different colors, it would be 8 factorial. However, if I just consider the purples, I could put, and let's say those three positions I put, so this position, this position, this position, I put P1, P2, P3. I could also put P1, P3, P2, just switch these two. Or I could go P2, P1, P3. Or I could go P2, P3, P1, or P3, P2, P1, or P3, P1, P2. I think there's 6 different ways I could reorder those. Well, of course there are, because of the purples, how many different ways can I choose, or how many different ways can I choose the first one? 3, then 2, then 1. We get 6. So in every one, this is just one distinguishable permutation. But I could view this 6 different ways just by switching the purples. So those are all counted into here, so I have to take that 8 factorial and divide it by 6. Where did 6 come from? 3 factorial. Also, the blues, I could get exactly this permutation 2 different ways just by switching the blues around. And that's how many choices for here, blues? 2 times 1. And you could actually make an argument. We could also put in a 1 factorial and a 1 factorial and a 1 factorial, but of course that's 1. There's our distinguishable factorials. It's how many, or permutations. How many ways can I rearrange it? 8 factorial. But we have to divide out the ones that we've multi-counted. And I'll refer to this as a banana problem because it's very similar to what we're about to look at with the Mississippi problem. Find the number of distinguishable ways we could rearrange the letter. Think of these as Scrabble tiles. We could rearrange the letters in Mississippi and end up with a different, end up without the same exact appearing, we'll call them words. When we rearrange it, obviously they're not necessarily going to be words. But it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 factorial ways we can arrange them. But I notice I have 4 I's that can be arranged 4 factorial ways, 4 S's, and 2 P's. And that, when you go to calculator, will give us the number of distinguishable permutations. The number of permutations is 11 factorial. But the number that we could distinguish from one another, we have to divide out, flipping the S's around, flipping the I's around, flipping the P's around. All right, here we go. 51 through 56. Use the formula to calculate. This will be more interesting if I call it 7C2. And it starts out just like a permutation. It's 7 factorial on 7 minus 2, 5 factorial. But we have to ask ourselves, we have to say, hey, all the orderings are figured into this. All of the different orders are figured, and we chose 2. How many different ways can I order those 2 choices, then 1 choice, 2 factorial? So if this was 7C3, it would be 7 factorial on 4 factorial. That's our permutations that have the orders counted in. I don't want to count the orders. How many ways can I rearrange the selection of 3 factorial? So anyway, this would be our solution to that one. And we can go to calculator on that. Okay. Oh, actually, I'm going to go ahead and do this. So this is 7 times 6. The 5 on down cancels, because we're supposed to actually find that value. The 5 on 6, 7, 6, the 5 on down cancels. I still have a 2 times 1. Those reduce to 1 and 3, and we end up with 21. But we have technology, SpongeBob, so we can go ahead and figure this one out. On clear combination, we can just go ahead. You can actually enter the 50 first if you like. You don't have to, but we go to alpha window or math probability, and there's combination 50, combination 6. How many ways can I choose a group of 6 out of 50? And that's a lot of ways. 1, 5, 8, 9, 0, 7, 0, 0. Please put commas in when you get numbers of that size. Right, all the possible selections of 3 letters. And then so I'm choosing 3 letters, But then it says, hey, the order doesn't matter. I'm choosing a subset from a big set, combination or permutation. This is combination because the order does not matter. So I'm going to stay alphabetical. ABC, ABD, ABE, ABF. I'm done with the ABs. So ACD. I don't have to come back to ACB because I've already got ACB right here if the order doesn't matter. So ACD, ACE, ACF. I'm done with the ACs. ADE, ADF. I'm done with the ADs. AEF. I'm completely done with the A's. So I'm going to pick up with the B's. So there's a bunch there. I hope it gets better. Let's see. BCD, BCE, BCF. I'm done with the C's here. So BDE, BDF. Done with the BDs. BEF. Okay, not as many B's. Let's jump to the C's. Hope it gets better. CDE, CDF, CEF, excuse me, I'm done with the CDs, CEF, and I jump to the D's, and all I have is DEF. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. We have 20 of those, which ought to be what combination, 6 letters, so should be 6C3. Let's see if I have those 20. Let's go 6 alpha window combination 3, and we got 20. So I believe we got them all. A little bit too far zoomed in here. Sorry about that. Okay, you can answer 18 questions out of a total of 20 on exam. And how many different ways can you select the question? So we're going to select 18 out of 20. Now we have to try to figure out, does the order matter? Let's say it was I could select 4 out of 5, and I select A, B, C, D out of A, B, C, D, E. Is A, B, C, D the same selection of questions as D, C, B, A? Well, they haven't done anything to make me think that the order of these questions matter. So this is going to be 20, choose 18. It's just, is it combination or permutation? I'm going to claim combination because I don't believe the order matters. There's nothing they did there that implies that. So 20, alpha window. I could leave this for you to do, but choose 18, and we get 190. Let's look how easy that would have been. When these two numbers are close, it's pretty easy computation. See, I would go 20 times, well, do this. 20 factorial over 2 factorial times how many ways can I arrange the 18? 18 factorial. So that just gives me 20 times 19 stop over 2 times 1. Oh, that's just 10 times 19, 190. All righty, we're getting there. 3 points are not collinear. Or 3 points that are not collinear determine 3 lines. For instance, if this is ABC, I've got line AC, line AB, and line BC. Okay, there's 3. I don't get any more from those 3 points. But how many if I had 9 points? 1, 2, 3, 4, 5, 6, 7. Trying to make these non-collinear. If I draw from this point right here, if I call this first point A, I could get 1, 2, 3, 4, 5, 6, 7, 8 lines drawn in. And then from this one, this line's already drawn. There would only be 1, 2, 3, 4, 5, 6, 7. So there'd be 7. And it stands to reason 2 of the lines have been drawn to here. 6, 5, 4, 3, 2, 1. And by the time I got all the way around to here, there'd be none left for there. So this is 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1. We don't have a special key on our calculator. We just have to do that. Let's see. That's 9 and 9 and 9 and 9. 4 9s, 36. But, as you might guess, better way to do this. What constitutes a line in terms of points? Any 2 points. I want to know how many selections of 2 points I can get out of 9. I have 9. How many selections of 2 can I get? Now, does choosing A, B give me a different line than choosing B and A? Nope, same line. It would be different if it was rays. A through B versus B through A. Sorry. But the order doesn't matter is what I'm saying. C9, 2. Could we really do that? Let's go 9 alpha window combination 2. And there it is. There's our 36. So what constitutes a line? Any 2 points. I want to jump down to 70. The number of possible interpersonal relationships increases dramatically as the size of the group increases. Determine the number of different two-person relationships. Same exact problem. There's a famous handshake problem. We could say, well, a handshake could just determine interpersonal relationships. How many handshakes can 3 people, how many unique handshakes can 3 people make? Well, A could shake B, B could shake C, and A could shake C. So I'm looking for two people. I want to choose groups of 2. How many groups of 2 people to handshake or have a relationship can we have? I have 3. I'm selecting 2. Does the order I make, if I choose Bob and Jeff, is it the same? Does it represent the same relationship as Jeff and Bob? Yes. So the order doesn't matter. It's combination. And that is, I'll leave that to the viewer, but boy, we should know that one. All right, and so this is just 8C2, and C, out of 12 we're choosing 2, order doesn't matter, and D, out of 20 we're choosing 2, same exact problem as up above. All right, number 68. A law office interviews paralegals for 10 openings. We got 13 with 2 years experience and 20 with 1 year experience. How many combinations of 7 paralegals with 2 years of experience and 3 with 1 year of experience are possible? Well, I need 7 of the 2 years. I'm choosing 7 of these 13. 13, choose 7. Does the order I choose them in matter? Might matter if I said the first paralegal is going to be in the office next to mine, the second paralegal is going to be in the basement, the third is going to be in a closet. You know, I'm not distinguishing those positions, so that's combination. And likewise, out of these 20, we're choosing 3. But I want to choose all 10. It's now this has turned into a closet problem. I have this many shirts and this many pair of pants. How many outfits do I have? Times. And the theme of the day, I'm not doing some of the calculations for you. All right, 72, especially 72B, will really make a nice point for us here. We got 30 flat screen televisions. Out of those 30 flat screen televisions, 3 are defective. So we got 3 bad ones. We must have 27 good ones. We're going to receive 4. Of these 4 units, how many ways can we receive all good units? So if I'm going to go all good in A, I'm not really selecting. I can't really select from the 30 because some of those, if I select 4 from 30, sometimes I'd get bad ones in there. I want to just select from 27. I'd refer to this as just a partition. You know, it's like a deck of cards, partitions into hearts, spades, clubs, diamonds. This deck is good and bad. I want to only select 4 from the good ones. So I'm choosing, from 27, I'm choosing 4. Is there anything that implies the order that I choose the TVs in matters? No. Now, ands and ors. This is going to be a good one. Oh, actually B, not B, it's C that's going to be the really good one. Now we want 2 good units, but we're still selecting 4, which means I need to select 2 of the 27, and I need to select 2 of the 3 bad ones. But C, this is it. At least 2 good ones. So I'm going to just formulate this in my head. What does that mean? I could have 4 good and no bad, or 3 good and 1 bad, or 2 good and 2 bad, and I would win. If that's my goal, is to get at least 2 good units. So how many ways can that be done? 4 good, we ought to know now, is 27C4 and times 0 bad, that's 27C0, which is really 1, so you wouldn't have to write that one down, or plus 3 good, 27 choose 3 of the good ones, and times 1 bad one, choose one of the 3 bad ones, sorry, one from that partition, or plus 2 good ones, so out of the 27 I want 2, and times 2 bad ones out of the 3, can't get through this, out of the 3 I want 2. So that's a really good visual, I believe, of how we handle ands and ors. Ands times, ors pluses. And leave that to you. And there is our assignment. And let me know what I can help with.